Hello everyone, this is DA from Academy, and this video is about the examples of the convex sets, as the definition of the convex set has been delivered in one of the previous videos. So this one is about its examples. So let's start it. So the very first example that we are going to see is for any subspace S of that linear space N, and for every element of that linear space N, this set X plus S with X is added in every element of that S, that is a subspace of that linear space. So this set is convex. This is the claim, and now we're going to prove that the set is a convex set. So we'll use a definition here in order to prove this. So let's take two elements from this set and name them U1 and U2. As they're taken from this set, so their structure must be of type this, where S1 and S2 are taken from this subspace S, and X is obviously from that linear space. So, and we have to take a constant in between 0 and 1. So let's take a constant alpha. Now the definition of the convex set says that alpha U1 plus 1 minus alpha U2. So we're going to put the values of U1 and U2 here. So this is equal to alpha, this is X plus S1, and alpha 2 is X plus S2. So we're going to put here. We get this. So now we're going to manipulate this. That alpha times X plus alpha times S1 plus X plus S2 minus alpha X minus alpha S2. So what we're going to do is here that we'll take the values of common thing, that is firstly alpha X, and we have minus alpha X. So we'll eliminate this. We have alpha S1, we have minus alpha S2, and so we're left out with four elements: alpha S1, X, S2, and minus alpha S2. So in order to make it a form of this convex form, so we'll take that X here and we'll take S2 common from these two elements. So now we have this form: alpha S1 plus X, and S2 is coming out from 1 minus alpha. So if we take the element alpha S1 with alpha 1 minus alpha S2, so this is just a form of this alpha U1 1 minus alpha U2, as S is the subspace of the linear space N, and by definition any subspace of a linear space is convex. So alpha S1 and 1 minus alpha S2 belongs to that S. So we can figure out, or we can write in place of this thing an element of that subspace, just like this, that S is equal to alpha S1 plus 1 minus alpha S2, and this whole thing is a member of that S, the subspace of the linear operator. So we have X plus S is a form of this set X plus S, and this is an element of this set. We can say that X plus S, or for any subspace of that linear space, this set is a convex set for every X taken from that linear set, or we can say that linear space. So we have proved now that for any subspace S of that linear space, and this type of set where X taken from that linear space is always a convex. So now moving toward another example. Now second example is about the linear transformation. So assume that T is a linear transformation from one linear space to another linear space, and C is a convex subset of that linear space N. Then transformation on C, that T of C is also convex. So let's start this proof. Algorithm is same, that we have to take two elements from this because we are going to prove that this is a convex set. This transformation is convex. So we'll take two elements from T of C and name them U1 and U2. As this is the transformation on C, so we have to take two elements from this convex set, convex subset of that linear space. So let's take C1, small c1, small c2 element from this convex subset. And the structure of these U1 and U2 will be now this, that U1 is transformation on C1 and U2 transformation on C2. And then if we take any alpha in between 0 and 1, we can write the definition of the convex alpha U1 plus 1 minus alpha U2. Now substitute the value of U1 and U2 here. We can get, as T is a transformation from one linear space to another, so T is a linear transformation, so we can get this alpha inside of that C1 and this thing as well here. We have, again we'll use the linearity of that T. We have as C1 and C2 was taken from that convex subset, and this is just an element of that C as well. So we can say that alpha C1 and 1 minus alpha C2 are elements of that C, and we can just write an element of C here instead of all of these things. So put C instead of all of these, and this is of course an element of that transformation T of capital C. So this proves that this transformation T of C is convex when T is taken from one linear space to another. So moving toward another example. So the third example is about two convex subsets of a linear space. So let K and L are two subsets of the linear space N. Then the set is also convex. So the given thing is that we have K and L are two convex subsets of that linear space, and we're going to prove that this K plus L, the subset of this thing, the set of this thing of the subset, is also convex. Again, we'll take the two elements of this thing because we're going to prove that this is a convex. So let's take U1 and U2 element from this K plus L, as we have to take elements of K and L as well. So let's take x1 and x2 from K and y1 and y2 from L. So for any alpha in between 0 and 1, we can write the definition of convex here, and we'll substitute the values of U1 and U2 here. So we can get alpha U1 is x1 plus y1, and U2 must be x2 plus y2. So we can manipulate this. We get alpha x1 plus alpha y1, x2 plus y2 minus alpha x2 minus alpha y2. So we have to make in order of this form. So in order to make the definition of the convex, in order to make it applicable for the definition of the convex. So what should we do here is that we'll take alpha x1 and x2 and minus alpha. We'll take out alpha x1, x2 and minus alpha x2 first, and then the remaining items of y1 and y2. So we can take out x2 here from here and y2 from here. We have, as K and L was a convex subset of N, so alpha x1 1 minus alpha x2 is indeed an element of K, and alpha y1 and 1 minus alpha y2 is an element of L. So this is an element of K, this is an element of L. So we can write here x plus y, where x and y belongs to K plus L. So we have proved that for any convex subsets here K and L of a linear space N, this type of set is also convex. So this is for now. Looking for more such videos, and you can subscribe this channel in order to watch more upcoming videos. We will meet in the next video. Till then, take care. Goodbye.